Okay, good morning, everyone. We will start in a minute or so. Okay, good morning. I hope everyone can see the screen. So today we will sort of begin with Markov chains.
So have you started the lecture yet?
Just now.
Just now.
Just now I am just opened
Okay. Okay, sir. Okay, sir.
So for Markov chains and this thing that these two books are kind of general references. Don't strictly go by that because they may considerably deviate also. But anyway, the notes will be given. So these two are fairly standard books. Note it down if you want to. So today we will be sort of beginning with Markov chains. So before that, some general comments concerning stochastic processes. So some of you might already have come across these things. So situations or models such as which are subject to randomness and evolving with time. That is, there is a kind of evolution or dynamics and also randomness. And these are often modeled by a collection of random variables. And this collection of random variables is indexed by a parameter which may be generally viewed as a time parameter. Because so evolving means over time. So if that collection is indexed by 0, 1, 2, 3 like that, that is discrete time, such a collection of random variables is called a discrete time stochastic process. And a collection of the form x sub t, where t varies over the continuum, 0 to infinity, that's called continuous time stochastic process. So in this course, we will be confining to discrete time stochastic process and also taking values in countable set. And all the random variables are assumed to be defined on the same probability space, let us say omega fp. And taking values in the real line or the vector space or the real vector space or some suitable subsets of this. Generally, these subsets will be set of all integers or non-negative integers or points in R2 with integral coordinates, integer coordinates, and so on. Countable sets, and also discrete sets. That is, topologically, they are discrete. Note it down if you want to. Yeah, this is what I had said. In this course, we will deal only with certain classes of discrete time stochastic processes. So the time parameter space is 0, 1, 2, 3. Okay. So important aspects of this subject. See, often many of these, the random situations we are talking about might have come or arisen in other disciplines of study. Classically, of course, physics or statistical physics, and in modern day, these things, even economics, and also telephone industry. Telecommunications has been a big contributor, and also various aspects of science and engineering, and so on. Okay. So the first thing is, if you are modeling that, you have to understand the nature of the interrelationship among these variables, random variables. See, for all this family of random variables, they are just on quite unrelated and no completely independent of each other and so on, then it's not going to be of much use, because we would like to know how these things evolve, which means something there should be some kind of a relationship. So that is why the nature of interrelationship among these random variables. Now, when you sort of just try to study the situation as it occurs.
Sir, I have a question.
Yes.
So in a discrete time stochastic process, generally these random variables xi, they are assumed to be not to be independent, right? Because
they may arise from independent segments.
Okay, but they are generally not independent.
If it is completely, they are going to be independent, then that is just chaos.
Just chaos. Okay, fine.
We won't get any information.
Okay, okay.
I mean, even if you know, you have observed the process for millions of years, you don't know what might happen the next time. Okay. So now when we want to study these things, understanding, and also our purpose is to investigate or study, which means the tools available to you to study, which will generally be coming from mathematics. So the thing should be mathematically amenable, which might involve certain simplifying assumptions. Yeah, to sort of make this point a bit let me mention something which has all of you might have known. Many of you would have come across physics at some stage or other. So the laws of motion and so on. So when Galileo was studying those relationships, so as you know that he dropped two weights of, differing weights, metallic weights from the Tower of Pisa, because it was leaning, and observed that they seem to reach the ground at the same time. So he made the assumption that the air currents and things like that do not have any impact on that. That's a simplifying assumption, because that will not happen if you happen to drop a feather. For a feather movement, the air current does matter a lot. So to understand certain things, certain simplifying assumptions will have to be made. So you should always keep in mind that these models are a kind of approximations, because so how good those things are, that only time can say. Okay. So mathematically, make it mathematically amenable, certain simplifying assumptions one makes. Because if you formulate the thing with all the parameters, taking into account all the effects, all the causes, possible causes and things like that, then just might be just too difficult to handle. And once you formulate a model and try to study it, one of the main aspects of this subject is to study the asymptotics of the model. That is, what happens as the time parameter goes to plus infinity. And in many situations, it may be possible that as the time parameter goes to infinity, there could be, the model might sort of settle down to some pattern. So which might be easily observable. So supposing that model has been observed or studied, or that situation has been observed and studied for quite some time in the past. So then you can make predictions based on the asymptotic behavior. That is, asymptotically, supposing you know that it's going to stabilize to a particular situation or a particular distribution. And then let us say at the time n+1, you sort of make a prediction that this is what one might expect to get with certain probabilities. And then that can be perhaps be experimentally checked. So this would in turn help in assessing the relevance and usefulness of the model. Because if what you predict and what you observe happen to be in reasonable agreement, then you know that you have got a reasonably good model. If there is a wide disparity, that means the modeling is not all right. Something important is being overlooked. And of course, this also has inherent mathematical interest. So all the models which we will be studying are sort of time test. That is, they have been found to be useful. Okay, so they will just give the mathematical model and try to study the asymptotics. And also the related to study the asymptotics, we need to go through certain other kind of things in that process. Okay. Yeah, so please note it down if you want to. It is just, you don't really have to note it down, and when I supply the notes, you will see. Okay, now it is a human limitation that it is not possible to describe precisely the joint distribution of more than finitely many random variables. That finitely many could be 10 at a time, or 20 at a time, or 100 at a time, or million at a time, but still it is going to be finitely many. So we will sort of take it that a stochastic process is well defined or completely specified if from the description given and the assumptions in the model, we can find in principle the distribution of x sub n1, x sub n2, x sub nk for any n1, n2, nk in the parameter space, and for any k equal to 1, 2, 3, etc. Any finite k. So if this is possible, we will assume that the stochastic process is well defined. And it is the measure theory will sort of take care of why this is sort of sufficient. Okay, that we will not go into. That would mean on which, for example, for studying normal random variable and things like that, you have to understand the real line. And there are a lot of problems with that's why even the term sigma algebra has been introduced and so on. So similarly, this would involve what kind of space to choose. This will be in general can be infinite dimensional spaces, and there what kind of that the measure theory will take care of.
So sir, here by distribution we mean joint distribution, right?
Joint distribution, yes, yes.
Joint distribution.
The distribution of any such vector. In principle, it should be possible to get it. Even this computationally cannot be very simple for arbitrary these things. Okay. Okay. So that is. So the description we give and also the assumptions we make, so that will sort of help in this. And if that is done, we will be satisfied that stochastic process is completely specific. Okay. So now some general remarks. Let since we will be dealing with only a discrete time stochastic process, let Xn be a discrete time stochastic process. These are all random variables are defined on some basic probability space omega fp. So for any little omega in capital omega, you consider the sequence x0 omega, x1 omega, xn omega, and so on. That sequence is called a sample path. That is, this is the path taken by the process evaluated at this little omega. And since we are wanting to investigate or understand the relationship between various xn's, one of the modeling assumptions which is very reasonable to make is that to depend or to find the distribution of xn, perhaps it would be enough to know the distribution of all the xk, k less than or equal to n minus 1. I mean, what it basically means is that to sort of find what is going to happen at xn, the past history of the process will be helpful. See, to predict what is going to happen, let us say at x100, if you require the knowledge of x200, then that is not a good model. So this is a very reasonable modeling assumption. Okay, note it down. So with this preliminary comments, let us say what is a discrete time Markov chain. So omega fp is a probability space. S is a countable set. Usually S is the subset of the integers or the integer lattice or R and so on. It can even be a finite set. So let x0, x1, etc. be a sequence of random variables on omega, taking values in this S, this countable set S. So xn, the collection xn, is a discrete time stochastic process taking values in S. So the process is said to be a time homogeneous Markov chain, or we will simply say Markov chain, with state space S. If for any n greater than or equal to 0, any time point n, and also let us say I sub 0, I sub 1, I sub n minus 1, I, j, these are elements of S. We have what I'm going to say next. Note it down if you want to. The Markov property holds. Markov property is basically what it means is forgetting the past. So the conditional probability say in this picture, we will consider time points 0, 1 up to n-1 as past, and n as present, and n+1 as future. Okay. So conditional probability that x n+1 at time n+1, we process it in state j, given that and the various past time points and also the present, it has been x0 at I0, x1 at I1, and xn-1 at in-1, and xn at I. So this conditional probability is same thing as predicting xn+1 probability xn+1 at j given just the present.
So sir, can you go to the previous slide once again? Yes, it's fine. Okay.
Okay. What this means is to predict what is going to happen at time n+1, the knowledge of what happened at time n is enough. The past is irrelevant. Of course, note that if this is going to be something different from 0, it should happen that this probability of this all these things happening up to time n, that set has positive measure, positive probability, and this is sort of this will contain this, therefore this will also have positive measure, positive probability. So in other words, if it is a Markovian type of process, if somebody has been observing it for 10 years and he has all the knowledge, and someone just now comes and starts observing, the man who has been observing over the last 10 years, he's at not any great advantage. Let us not put 10 years, let's say 10 minutes. So this is the crucial property, and we will make to make sort of life simple for ourselves, we will make the time homogeneity assumption. That is, probability xn+1 equal to j given xn equal to I is same thing as probability x1 equal to j given x0 equal to. So this can be considered as at x0, if it is at I, at time 1, the probability of it being in j. This is the one-step transition probability. And that one-step transition probability is independent of n. That is what time homogeneity assumption tells you. This time homogeneity assumptions make notations much simpler, and even the discussions quite much simpler, and so on.
So sir, for a given value of I comma j, one-step transition probability is same. I mean, it doesn't depend on n.
Yes, yeah. It is not that the processes which do not have this time homogeneity are not important. They are important, but that will not be in this course.
Okay, so basically in this course, we will only deal with time homogeneous Markov chain.
In this course, see, I am a simple man. We will start only simple things. Okay.
No, in this course, we will only deal with time homogeneous Markov chain, right?
Yes, sir. And it itself will keep us busy. So since we will be considering only time homogeneous Markov chains, and also we are all lazy people. So to sort of to minimize of our efforts, we will just say Markov chain. So when we say Markov chain, it would mean a time homogeneous Markov chain.
Sir, I have a question. So for a time homogeneous Markov chain, can we say that if we consider two-step transition probability or three-step instead of one step, so that will also be same independent of n?
Yes, yes, yes. But then it will depend on 2 and 3, things like that. Yes, you will see soon. Some patience. Note it down if you want. Okay. Noted it down. We will now define what is meant by a stochastic matrix or a transition probability matrix. So by a transition probability matrix or a stochastic matrix, we mean a square matrix Pij, where I and j can vary over a finite set or even a denumerable set. We retain the same terminology. Satisfying each of these Pijs are non-negative for all and j, I and j in S. And it also has the property that this Pij for any row, if you sum over all the row elements, that is equal to 1. That is for any I in S, summation over j varying over S, Pij is equal to 1. So if this happens, such a matrix is called a stochastic matrix. And in this setup, this S is called the state space, and the elements of the state space are called states. Incidentally, stochastic matrices are also studied by matrix theorists. Of course, an obvious example is staring at in our face, namely from a Markov chain, time homogeneous Markov chain. Let Xn be a time homogeneous Markov chain. Denote by P sub ij the one-step transition. Probability x1 equal to j given x0 equal to I. So we define Pij by this for all I and j in S. So this is a stochastic matrix is clear because they're all non-negative. And now supposing xi is in I, state I at time 0. At the next state, it will have to go to one of the states in j. It could be j can be I itself, or it can be, but it will go, it cannot go outside that. Yes. Therefore, summation Pij over summation over j is 1. So since this matrix, we have got it out of a time homogeneous Markov chain, this P in this context will be called the transition probability matrix of the Markov chain Xn. So time homogeneity already, see, you can see the advantage. If it is not time homogeneous, for each every n, you will be getting a matrix. So you will have infinitely many matrices. Okay, please note it. Okay. It's an exercise. So let Xn be a Markov chain with state space S and transition probability matrix P. So let mu be a probability measure on the state space S. Since this S is a finite or countable set, that numbers we can conveniently write as mu sub I. So mu sub I is basically mu of the set singleton I. And also, since it's assumed to be a probability measure, summation over all the i's varying over S of mu I is equal to 1. So for any n and any I0, I1, In in S, you can easily see that probability x0 is at I0, x1 is at I1, and xn at In is going to be mu at I0. So that is the probability of this element. And then probability of x1 equal to I1 given this. So that will be P sub I0, I1. And because of Markovian thing, for knowing what has happened at x2, you need to know only x1. So the next step, probability of x2 equal to I2 given x1 equal to I1, or given this, all this information is same thing as given x1 equal to I1. So that is P I1, I2, and so on. So in other words, use this mu is a kind of initial distribution of the process, the distribution of x0. If you know that and the transition probability matrix, you are able to know the probability distribution of the vector x0, x1, xn for every n. The joint probability mass function of x0, x1, xn for every n. So this kind of simple observation already tells you that if you know mu and p, you can get hold of the joint distribution of x0, x1 up to xn for every n. Suppose x is 10 million, even that you can get, but only thing is that might involve a laborious computation to know it.
So basically, all you need to know is the distribution of x0
and p. This is even more important.
Okay. Okay.
Mu can be different. Mu, you can even do things with the Dirac delta distribution at each I and so on. But the crucial nature of the Markov chain will be governed by P. So what I was mentioning in words, I have written it. Thus, the distribution of x0, x1, xn can be obtained in terms of mu and p. That is, in terms of the initial distribution, mu, and the transition probability matrix, p. So in view of the previous slide, supposing you want to find the distribution of xn1, xn2, xnk, let us say x3 and x10. So that can also be done. In that case, x3 and x10, if you want to find, you find the joint distribution of x0, x1, x2, etc. up to xn. That will be an object like this. And in this, sum over all the other variable things concerning other variables. That is I1, I2, I3 will be important because x3 you want. So I0, I1, I2, and also up from I4 to I9 or something like that. So that kind of, by taking the suitable marginal, finding the suitable marginal distributions, you can find. Marginal meaning need not be one-dimensional marginal. Let us say if you have a 10-dimensional random variable, some 3-dimensional marginal. That means you sum over the remaining 7 variables. So in principle, one can find the joint distribution of xn1, xn2, xnk for any n1, n2, nk in the time parameter space and for any k. So any finite time points. So that is, once the initial distribution and the transition probability matrix are given, all finite dimensional distributions of the Markov chain can be obtained in principle. So another simple.
Sir, I have a question. Can you go to the previous slide? So here, when you're trying to find joint distribution of xn1 to xnk, so
Yeah.
how can we find the distribution of xn1 from x0?
No. You see x1 to x, this formula. See, this will give you for whatever possible values of I0, In, you can get that.
Yes.
So once you have the distribution of x1, x0, x1 up to x10, you can, from that you can find the distribution of x3, x9. That's
Yes.
all I'm trying to say. See, if you know the joint, the probability mass function of y1, y2, y3, from there you can find the joint distribution of y1, y3.
Yes.
Like that, that's it.
Okay, I got it.
Okay. So this basically says that not just the one time point in the future, if you want to know about the finitely many time points in the future, that is n+1, n plus m. So if you know the entire past up to n-1, that is irrelevant. Only what you know at xn should matter. And because of time homogeneity, this equality becomes this equality. And all these things are So all these things. Okay. Because x0 equal to I means you are asserting that at time 0 it is at I, which means the mu measure here is the degenerate measure at time. Note it down. Okay, this is the last slide for today.
Sir, what is small delta of I?
Degenerate measure at I, that is a probability measure which assigns the mass 1 at the time point 1, the singleton set I, and everywhere else it is 0.
Okay. Okay.
So next, we will give some examples of Markov chains. That will be the next class. So the Markov property will be inherent in the description of the situation. In other words, we will generally, it will be part of our modeling assumption. Probably from the insight given by the domain experts, the physicists or economists or engineers and things like that. And of course, in some cases, it might be derivable from other assumptions. So in view of the remarks earlier, it is enough to specify the transition probability in each example, because the initial distribution is in your hands. So basically, we will begin with the examples in the next class. We will give some examples which are not just isolated examples. They form sort of many this kind of example, that kind of the processes having that kind of a property, or they themselves have become intense objects of study. Textbooks are written on that, or textbooks or monographs are written on such topics. And also we will look at certain specific kind of examples. So I shall stop here today. And if you want me to go to any of the previous slides or something, I can go back. So if not, I will soon end the session. Okay.